All right, so here is part two of the lecture. Just a second. So what we're going to be talking about now, we've got basically 2.5 more things to talk about. The first of which is talking about solutions, and that is the idea of molarity. Molarity, or molar concentration, is denoted by the capital letter M and is the number of moles of solute per liter of solution. Now, this provides a relationship among molarity, moles of solute, and liters of solution. Molarity is denoted by this capital M is equal to moles of solute over liters of the solution. Now, to capture this in a question, we've got this right here. A solution is prepared. I do have the calculator. A solution is prepared by dissolving 45 grams of NaClO in enough water to produce exactly 750 milliliters of solution. What is the molarity of the solution? So basically, this is a solid. This NaClO is a solid. And somebody got like a graduated cylinder or something. And they put that solid in here. And then they added water. They added water up to this line. That's about 750 milliliters, which for the purposes of this, a milliliter, you need 1,000 milliliters to make 1 liter. So this 750 milliliters, we're going to convert that to 0.750 liters. Okay, so what we need to figure out is what is the concentration of the solution? How many moles of this NaClO in this 0.750 liters of water? Okay, so the first thing that we need to do is take our 45 grams of NaClO, and we need to figure out the molar mass of this. Okay, so for the periodic table, I've got that open in another tab. And I'm going to tell you that sodium has a, oh man, I believe sodium's like 23 grams per mole. pt2.com. Yep. Sodium is 23 grams. Chlorine is 35.5. And oxygen is 16. So our total molar mass of these three things is 23 plus 35 is 58 plus 16 is 64, 74. So we have 74.5 grams of NaClO is 1 mole of NaClO. Now we take 45 and divide it by 74.5, you would get, well, 45 is less than 75, so we have less than 1 mole. We would end up getting approximately 0.604 moles of NaClO. So we can take that number and throw that right here. So moles of ClO divided by the volume in liters, well, we've already figured out our volume in liters. So what we want to do is basically figure out capital M, which is 0.604 divided by 0.750. So 0.604 divided by 0.75, and we get a molar concentration of 0.81 molar. So that means there's 0.81 moles in a liter. There's 0.6 moles in 3/4 of a liter, or 0.75 liters. Okay, so that's how we do that sort of problem. We have to convert our mass into number of moles and then divide by the volume of our solution in liters. Okay, the next thing that we're going to do is dilutions. Talking about dilution. So if you think about or whenever I think about a dilution, I always think about if you had something like Dr. Pepper or something like that. And you took Dr. Pepper, actually, just a second, I've got an idea. Okay, everyone has a sense of what making a dilution consists of. And that's because they've had something that's diluted. So here I have two approximately equal volumes of an orange soda and water. Now, if I take my orange soda and I pour it into my water, what's going to happen? First of all, we can think about some of the physical properties. Is my orange soda going to taste as good? It's not. The flavor will be diluted. Second, there's sugar in here. There's artificial sweeteners in here. The amount of those artificial sweeteners will not go down, but the amount of those artificial sweeteners per total volume will go down. Why is that? Because whenever I take this and I pour it in here, the total volume of my solution will go up. Excuse me. Because if we called this 250 milliliters and this 250 milliliters, and I pour this into here, what's my total volume? My total volume is 500 milliliters. I think that we'll probably be able to see. Oh, that's bizarre. There we go. There we go. That's a strange look. It's still pretty robustly orange. Still smells the same. But from my original solution, let's say there's 10 grams of sugar in there. 10 grams per 250 milliliters. Now, if I want to drink all of that sugar, I have to consume 500 milliliters of sugar, or my 500 milliliters of solution. So dilutions are something that you have a little bit of an understanding for, and you probably can even kind of quantify them, but here we're going to put a formula to it. So dilution is the process in which a solvent is added to a solution to decrease the concentration of the solution. So I decrease the concentration of my orange soda by adding it to water. I should have added the water to the orange soda, but here we are. The number of moles of solute is the same as before. So the amount of sugar that is in my new solution is the exact same as was in my original solution. But my volume has changed. Since the number of moles of your solute equals the product of molarity and volume, we can write the following equation where the subscripts denote initial and final values. So M sub I, initial molarity, and V sub I, initial volume, is equal to M final and V final. So your molarity final and your volume final. Now to capture that, we have a solution, or we have a need for a 1.5 molar hydrochloric acid solution for a series of reactions. The only solution available is 6 molar HCl. What volume of 6 molar HCl must be diluted to obtain 5 liters of 1.5 molar HCl? So this question gives you, you've got 6 molar HCl. What volume of this needs to be taken and added to this new solution for us to have 5 liters at 1.5 molar? Okay, so the way that we want to do this is a little bit backwards. So that MIVI equals MFVF. So our final volume is going to be 5 liters. Our final molarity is 1.5 molar. Our initial molarity is 6 molar. So what we're trying to figure out is how much of this do we need? And so what we're going to do is we're going to say 6 times V sub I is equal to 5 times 1.5. So 6V sub I is equal to 7.5. divide each side by 6. V sub I is equal to, so calculator, 7.5 divided by 6 is 1.25. Now this is a volume, and what was the volume that we used originally? 5 liters. So we need 1.25 liters of the 6 to make 5 liters of 1.5 molar. All right. So the addition of water to an aqueous solution will result in a blank volume and a blank concentration. So basically this is saying if you have a solution and you add water to it, addition of water, so more water goes into this solution, that will result in a blank volume. So you're adding water to a solution. Solution has, so if I added water to this, what would happen to the volume? Would the volume go down? No, because I'm adding water to it. I'm adding more of a solution to it. And so the volume would go up. So my volume will result in a higher volume. So I'm going to scribble out C and D. Now, I've added water to this. What happens to the amount of sugar in here? Well, the amount of sugar doesn't change, but the volume changes. The volume goes up, the amount of sugar stays the same, but the amount of sugar per unit volume has decreased. So we are looking at a lower concentration. Okay, so dealing with solutions, I think, is pretty straightforward. It's important to kind of visualize the question that you're asked. Like this question right here is a pretty tricky question because you are not provided with, here's the initial volume, here's the initial concentration, make a new solution, but instead you're asked, well, you need to make this from this. So when you're given the from this, that's kind of, that is your initial information. You need to use that to translate it into your finals. Okay, elemental analysis and empirical formulas. This is our changing gears, and this is the last thing that we're going to talk about today. Elemental analysis and empirical formulas. Well, we already know what empirical formulas are. They can be determined from an elemental analysis. So your empirical formula was your lowest common denominator. An elemental analysis measures the mass percentage of each element in a compound. So the formula describes the composition in terms of the number of atoms of each element. The molar masses of the elements provide the connection between elemental analysis and the formula. So this right here, percentage of each element in a compound, it's basically like if you look at a compound that is C6H6O2, you have to figure out the total mass of this. And then you have to figure out what mass of it is carbon, what mass of it is hydrogen, and what mass of it is oxygen. So that then you can come back and say, well, it's 60% carbon, 10% hydrogen, and that would leave behind 30% oxygen. And so you can use those percentages to figure out the exact ratio. So this is the information that you would be given so that you can figure out that right there. Okay, now there's a process for doing this. The first step is you convert the mass of each element to moles using their molar mass. You divide by the smallest number of moles to get mole to mole ratio for the empirical formula. Now, when division by the smallest number of moles results in a small rational fractions, multiply all ratios by an appropriate integer to give whole numbers. So here we have a 100-gram sample of a white powder, and it's analyzed to find that it is 43.64 grams phosphorus, and it is 56.36 grams oxygen by mass. What is the empirical formula of these? First of all, you can look at these two quantities and add them up, and it comes out to 100 grams. What we need to do is figure out the moles of phosphorus. We also need to figure out the moles of oxygen. So the way that we're going to do that is by looking at the periodic table. The periodic table tells us that 1 mole of phosphorus has a mass of 30.974 grams. Then 1 mole of oxygen is 15.999 grams. Oxygen and phosphorus. Now, generally, you see me use those numbers and round them, like 31 or 16. But for this, we're going to be a little bit more precise because we're given a very precise measurement. So 43.64, what we're going to do is we're going to take that number and we are going to divide 43.64 divided by 30.974. And we will see that that is 1.40. You know what? I'm going to call it 1.41. Then we're going to take our other number, 56.36. We're going to divide that by 15.999. And that comes out to be 3.52. Okay. So basically what we've come up with is we've come up with a compound that is P sub 1.41 O 3.52. Okay. Now, when you look at that, one of the things that's a little bit tricky about this sort of analysis is that anytime you look at a whole number or a molecular formula or anything like that, you are dealing with whole numbers. So what we want to do with these is we want to take the lowest number here, 1.41, and divide each one of these by 1.41. And that's going to be 1.41 divided by 1 is 1.41 is 1. 3.52 divided by 1.41 is 2.5. So essentially now, rather than looking at it as that, we come up with a ratio that is P sub 1, O 2.5. Okay, those are much more favorable numbers. Those are more favorable numbers because 2.5, we can multiply each one of these by 2 and get a whole number. So I can say by 2, 2. And so we get P sub 2, O5. So the steps that you go through for this is you figure out the number of moles of each one of these substances. Then you relate the moles of each one of these substances to the substance with the lowest number of total moles. So we have 1.41. We divided both of our number of moles by 1.41. We ended up with this formula right here. And all that we had to do was, in order to get whole numbers, was we had to multiply both of the subscripts by 2. Because we knew that when 1 is a whole number, if we multiply that by 2, that's a whole number. 2.5, that's not a whole number, but if we multiply it by 2, we get a subscript of 5, which is a whole number. So P sub 2, O5 is the empirical formula of the compound. And we can't reduce that down, so we know that it's an empirical formula. Now, another way that you can see this sort of question is something like this. So cortisol is one of the major steroid hormones. It's a key factor in the synthesis of proteins. Its profound effect on the reduction of inflammation explains its use in the treatment of rheumatoid arthritis. So if you know someone who has rheumatoid arthritis, it's really painful, moving the wrist and lots of different everyday motions that we definitely take for granted. They generally have they have cortisol that their body produces, but then they also have cortisone, which is a shot that they'll take, or they'll take cortisol shots, I think, also. So we've got this compound that has a mass of 362.47 grams. Now, cortisol is 69.6% carbon, 8.34% hydrogen, and 22.1% oxygen. What is the molecular formula? Okay, so this right here, what's our molecular formula? Well, in order to solve this problem, we first need to figure out the molecular formula. And so what we're going to do is we're going to say, all right, this compound, we've been given percentages, but if we add all those percentages up, we would end up at just about 100%. So 69.6 plus 22.1 would be 71, 91.7 plus 8.34, that would get us to 92 plus 8 would be 100%. What we're going to do is we're going to say 69.6, but rather than a percentage, we're going to say it's 69.6 grams. We're going to say this compound is 69.6 grams of carbon. It is 8.34 grams hydrogen, and it is 22.1 grams oxygen. We'll take these different substances, and then we're going to figure out the number of moles of each one of them. 12.011 grams carbon is 1 mole carbon. 8.34 grams of hydrogen is 1.008 grams of hydrogen. Is 1 mole of hydrogen. Let me erase that. And then our last one, 22.1 grams of oxygen. 15.99 grams of oxygen is 1 mole of oxygen. Equals and equals. So 69.6. 69.6 divided by 12.011 is going to be, we have 5, we converted to 5.79 moles of carbon. And then we've got 8.34 divided by 1.008 is going to be 8.27 moles of hydrogen. Then our last component is oxygen. 22.1 grams of oxygen divided by 15.99 grams of oxygen. That means we've got 1.38 moles oxygen. Okay. This gives us a formula that's basically up at the top, 5 point C sub 5.79, H 8.27, and oxygen 1.38. Completely unfavorable numbers. So what do? We take that 1.38, we divide it by 1.38. So now we're coming up with a common denominator for each one of these. So we're going to divide each one of these numbers by 1.38. So this gives us CHO sub 1. Okay. 8.27 divided by 1.38 gives us, ooh, this is nice. 8.27 divided by 1.38 is H 5.999 or 5.992. Okay, 5.79 divided by 1.38. That's 0. That's not right. 5.79 divided by 1.38. That is 4.2. Okay. So looking at these numbers, this 5.99, we can round that up. We're going to round that up to 6. C 4.2 H6O. Now, what we need to do with this is we need to come up with something that we need to come up with a whole number. So if we have 4.2, we can't really round that down. But you know what we can do? If we double it, then we're at C 8.4. Okay. That doesn't really help a lot. What if we triple it? Then it's C 12.6. Quadruple it, C 16.8. But if we multiply it by 5, that would be C sub 21. That's a whole number. So we can multiply this by 5. If we do that, then we have to multiply that 6 by the hydrogen by 5. So it'll be 30. 5. So what we do to one atom, we just have to do to all of them. Now, is it completely wild and crazy to say C21H30? No, there are compounds that are massive like that, and that's not a problem. Now, the question is, what do we do with this? So let's go ahead and use this as our proposed, or our proposed molecule. We've got nice whole numbers there. I'm going to go ahead and rewrite it at the top here. C sub 21, H30, oxygen 5. Now this question, though, asked us for the molecular formula. Okay, so let's go ahead and take this empirical formula that we've solved for and figure out what our molar mass is. So if we do 21 times the molar mass of carbon, which is 12, we get 252. Hydrogen, well, that's 1, so that would be plus 30. Oxygen, 5 times 16 would be about 80. Okay. So 252 plus 30 plus 80 equals 362. Okay, so we did it. We figured out our empirical formula, and our empirical formula happens to be the exact same mass as our molecular formula. And so our empirical formula is our molecular formula in this case. Now, the trickiest part about this was that we went through a series of steps, and we started out with some wonky numbers, but those wonky numbers were kind of the right numbers. So sometimes when you get an empirical formula, it won't be the same as your molecular formula. And we'll see that here. So CH sub 2O is formaldehyde. It has a molecular mass of 30.03. That molecule is its molecular and its empirical formula. This compound right here, acetic acid, has a formula of C2H4O2. Molar mass is 60.06. Okay, well, the empirical formula for acetic acid is the molecular formula and the empirical formula for formaldehyde. But there's a difference between formaldehyde and acetic acid. One's a disinfectant and a preservative, and the other one is used for, well, vinegar. It's used for cleaning and tons of other things. Now, what we need to do is sometimes we'll have to you'll be given, for example, you could be given something like, you could determine the empirical formula and then be told, well, your compound has a molar or a molecular formula of 90.09. And then you'd say, okay, well, if my empirical formula is 30.03, I'm going to take my empirical formula and divide my molecular formula by that. And then I'd see that it's a 3 factor, or it has a factor of 3. So then you just multiply each one of these things by 3, by 3, by 3. And you get C sub 3H6O3. So here are some examples of compounds that have a empirical formula the same as formaldehyde, but are different. Lactic acid, erythrose, ribose. These are all compounds that have the same empirical formula, but are pretty different. Butyric acid has an empirical formula of C2H4O and a molecular weight of approximately 88 AMU. What is the molecular formula? Okay, so what we need to do is we need to figure out the empirical formula for this, which carbon is 12, so that's 24. 2 times 12 is 24, plus hydrogen is 4 times 1, that'd be 4, and then oxygen is 16. So I'm going to add all that up. 28 plus 16, 3, 4, 44. So now, if I want to figure out what the molecular formula is, I'll take the molecular formula divided by 44, and I'll see that my answer is 2. My ratio is 2. So that means that I take this and multiply it by each of my subscripts. So I can eliminate A as an answer. I can eliminate B as an answer. And actually, I need to eliminate C, because what I'm doing is I'm taking this right here and multiplying each one of my subscripts by that. So I'm ending up with C4, H8, O2. Answer option D is the only good answer there. All right. Well, I hope that was helpful for everyone. This is definitely valuable information. It's great exam material. If you have questions about any of this, please let me know. I'd be glad to help you out. Other than that, I hope you enjoy your weekend.